Okay, this is going to be the fourth video on how to find the volume of solids using cross-sectional areas. And if you haven't done it, I would definitely watch the first three videos, and it'll give you an idea of how we got to this point. Now, in this fourth video, we're going to use exactly the same boundary conditions that we used in the first three videos. But the difference is, in the first video, we did a rectangle. Second video, we did triangles, cross-sections. In the third video, we did semicircular cross-sections. And in this video, we're going to do cross-sections in the shape of a rectangle that have a fixed height equal to 3. Now, sometimes the book will give you a sketch to show you what it looks like, and if you use the sketch of this situation, the sketch in the book probably looks like this. The blue area here is the area of the base, and it'll show you what a single representative cross-section would look like. Now, to help you picture what the solid is that you're trying to find, let's go ahead and put that solid on here. So if you were to get the solid area, this green shaded area here shows you what the solid is that you're trying to find the volume of. Now, let's go ahead and just give you a better look at it. We'll remove the axis, and let's go ahead and take that, that rectangle out of there. So this is the solid, and your job is to find the volume of this solid, and you're going to do it by sticking a baseline in there and putting a single cross-section. And if you can find the volume of this single cross-section, then if you add up all the cross-sections that make up this solid, then you'll be able to get the volume of the solid. So that's going to be our job. So we'll go ahead and stick the axis back on there. And again, in most cases, it helps to visualize the problem with the green area, but you really don't need that green solid to work with. The important parts are going to be the rectangle and the base. Okay, now to solve the problem, we're going to follow the same 6 steps that we did before. And just to remind you, if you haven't watched the previous videos, I would watch them. But I suggested these 6 steps. The first 2 steps involve sketching the object. Then the last 4 steps are the steps that you use to actually solve it. So we'll run through these as we work through this problem. And let's go back to the thing again. Now, before you begin the problem, this 3-dimensional view will be given to you from your book, and a lot of students have trouble sketching this whole thing in 3 dimensions. So my suggestion, as always, is let this be the book sketch, but also give yourself a second, what I'm going to call a working sketch. So on your homework page, or on the test page if you're taking a test, rather than trying to sketch it in 3 dimensions like this, I would sketch it like this, looking at it straight down from the top. And you can get the same information off this little sketch that you can off this one, but it's a lot easier to draw. So my suggestion is switch to this form of a working sketch with an X and Y axis, and we'll solve the problem looking at this, and just use this one as a reference. Okay, now finally, back to the steps. Let's run through the steps and solve this problem. So the first step says this: sketch the base of the solid in the XY plane using the boundary conditions. So let's see what that looks like. Now the boundary conditions are these 2 equations in black up here. So x is equal to y squared and x is equal to 4. So using your working sketch, first of all, if you just made a rough sketch of x is equal to y squared, well, that's just a parabola that's symmetric about the x-axis. And if you sketched it, it would look like this. Now at this point, it's an open parabola, so you want to find some way to close it to restrict it to a certain region, and that's what the second equation is for. So the second equation says x is equal to 4, and that's just a straight line that goes perpendicular to the x-axis through x is equal to 4, and it would look like that. And now you've actually enclosed an area, and if you were to shade that area, it would look like this. So what this is, this area right here represents the shaded area of the base, which is what this is over here. So now you've got the base of your solid. So let's go back to our steps. And you've actually completed step 1. You've sketched the base of the solid in the XY plane. Now the next thing, sketch a single representative cross-section in the required geometric shape. So we just want to sketch a single cross-section. When we get it sketched in, this is what it would look like in 3 dimensions. But we want to make a kind of a rougher sketch over here on our little homework page, say. So first of all, starting with this one, the way you got this sketch in here, you came in and had a baseline. Then from that baseline, you drew a rectangle. So there's the baseline, which we want to put a similar baseline over here. So I'm just going to come in some distance x, and it's your choice. It's just a random distance x, and we'll go from here and say draw the baseline straight down to here. So there's the baseline, just like this one is. Then the book shows a rectangular solid that looks like this. So you want to sketch the equivalent of that rectangular solid over here. Now again, since it's all going to be freehand over here, it doesn't have to be great. It just has to give you a working sketch that you can work with. So what I'm going to do is go up like this. I'll go down like this. And again, this is just freehand, and over like this. Now that's what it would look like as a plane, but I actually want this thing to have some thickness to it because I want to find the volume of this. So I suggest that you also then add a little bit of thickness to your sketch. So again, my sketch is going to look like this, like this. I'll go like this, and I'll come down like this. And what that does, and I even go so far sometimes as shade these things a little bit. So I'll put a little shading on the edges of this. And this gives me a rectangular area, but it also has a thickness. And as far as your problem goes, that thickness is actually going to be dx. So dx represents the thickness, and then you'll have the area of the front of it. Okay, so we've got one representative cross-section. Let's go back to our steps. So you've finished step 1 and you finished step 2. You sketched a single cross-section. Okay, the next thing you have to do, you have to find the area of that cross-section. So you need to find a general formula for whatever the shape that you have is. So again, just in general terms. And I think I'll go ahead and put that right here. So I need the area of a rectangle. So for our problem, the area of a rectangle. So the area of a rectangle, and in the simplest terms, it's just the length times the height. So there is a general formula for the area of a rectangle. So back to our steps. So now we've got as a starting point. Now the next step, and this is probably the trickiest step in the whole problem, is you have to change that general formula into a specific formula for your particular problem and your particular sketch. So now you need to find the area of a single cross-section in terms of x. So let's see what that's going to look like. So now the next step is to change this general formula for length times height into your specific problem using the conditions that you're given. So we'll scoot back up here. Now the idea is this, is you've come in a given distance x, so from here to the base of your solid is x, and what you want is the length times the height of this rectangle. Now on this particular problem, it tells you that the height of the rectangle is a constant 3, so what that means is this height right here is 3. You know how tall the rectangle is. But the question is, the length of it would be, by our sketch, it would be this length right here. So that's going to be the length of the rectangle. But the question is, what is it? Now again, going back to your sketch, if you were to just look at this point right here, it goes over a distance x and it goes up, this little distance right here, by my sketch is just whatever y is. Now, since the parabola is symmetric about the x-axis, then this distance right here would also be y. So if I were to add those two together, the length of this side would be 2y. So now what I've got here is the length of a side in terms of my sketch, which is 2y. So I know that the length is 2y, and I know that the height is 3. So if I were to multiply those together, I would get 6y. And what this is, I think we'll scoot down just a little bit. This is going to give me the area of the cross-section, but it's going to give it to me in terms of y. Now what I need is the area in terms of x. So I found the area of that cross-section, but I've got it in terms of y. So let's go back to our steps again. Now the problem is going to be this. When you evaluate the integral is with respect to x, so all the terms in the integral have to be in terms of x. So your next job is to change this area from an area in terms of y into an area in terms of x. So let's see how to do that. So we'll come in, and now it's all going to be based on, right now you've got this, the area in terms of, I think I'll put a little box around it here, the area in terms of y is 6y. So to change it in terms of x, come back up to your boundary conditions, and you need something that relates x to y, and use this boundary condition of x is equal to y squared. So we'll bring that down here, and starting with x is equal to y squared, take the square root of both sides, and you would have the square root of x is equal to y. And you'll use that over here. So now you know y is equal to the square root of x. So go back to this equation and replace y with the square root of x. So what that gives you is that it's equal to 6 times the square root of x. And I think I'm going to do this. I'm going to change that into 6 times x to the 1/2. And this is going to be the area of the cross section. So that's the area of the cross section. But in this case, in terms of, and this is important, so it's all in terms of x. So now you've got the area of the cross section in terms of x, and step 4 is completed. So let's go back and take a look at our steps. So you've got step 4. You've got the area of the cross-section in terms of x. The next thing says, now, determine the limits of integration. And this you'll get from your sketch. So let's go back and take a look at our sketch. So what happens is, in the sketch, now, dx runs with the x-axis. So I'm going to integrate this thing from here, starting at x equals 0, and you can get this right off your sketch, and I'm going to go all the way over to here. And that's going to be where x is equal to 4. So the limits of integration are from x equals 0 to x equals 4 with respect to x. So we've got the limits of integration. Let's go back to our sketch. And the last thing says this. We know what the cross-sectional area is. You know that it's all with respect to x. That's the thickness of a single cross-section. And now you know you're going to integrate it from 0 to 4. So now it's just a matter of plugging everything into the integral and seeing what the volume is. So we'll go back over to here, and let's go down to our sketch. And we'll start with this. So the volume is equal to, now it's the integral from 0 to 4 of the cross-sectional area. And again, we'll kind of quickly go back to the general formula here. It's the cross-sectional area in terms of x times dx. Well, we showed that the cross-sectional area in terms of x is 6 x to the 1/2, so this is going to be 6x to the 1/2, then the whole thing dx. So it turns into a fairly simple integral. Now we'll go ahead and bring the 6 to the outside and make that be 6 times the integral from 0 to 4 of x to the 1/2 dx. And that's going to become 6, and when we find the antiderivative, it would be x to the 3/2 divided by 3/2, evaluated from 0 to 4. Now, you can take this and make it be 6 and bring the 2/3, turn it upside down and bring it to the top. This would be 2/3 of x to the 3/2, evaluated from 0 to 4. So if you did this, 6 times 2 is 12, divided by 3 would be 4. So you'll have 4 times x to the 3/2 from 0 to 4. And just plugging this one in, this would be 4. Then you'll evaluate it from 4 to the 3/2 minus 0 to the 3/2. And then finally, this would be like having 4 times, and change this to square root of 4 cubed, which would be 4 times 2 cubed, 4 times 8, which would be 32. So when you finally get finished, the volume of that green solid is going to be 32 cubic units, whatever that is. So let's go back up to the top of our picture now and see where that looks like. So what you've actually done, now that you've got this thing finished, we'll put the green solid back on there again and remove this red axis. You found the volume of this green solid to be 32 cubic units. And just real quickly, let's run through the steps one more time. Let's go back over to our steps here. The first thing you do is sketch the base in the XY plane using the boundary conditions. Then you sketched in a single cross section. Then to find the volume, and I think we'll go back to our picture. So you've got this single cross section right here. Then to find the volume of the single cross section, you came up with a general formula. So the beginning of the whole problem was just this general formula for the area of a rectangle. Then you had to change this general formula into a specific formula for your problem. And that's what this step 4 was. So change the area of a single cross section and put it in terms of x. And that's what we did in here. So you found, first of all, you found the area in terms of your sketch, would put it in terms of y. Then to change it from area in terms of y into area in terms of x, you used the boundary conditions, and that put it in terms of x. So now you had everything that you needed. You can get the limits of integration from 0 to 4 off the sketch, and then finally it's just a matter of plugging it into the formula, and the formula is the area of a cross-section in terms of x times the thickness of that cross-section evaluated from whatever the limits were. And when we went back to our sketch again, then the work, you just plug it in, evaluate the integral, you get 32, and that 32 is the volume of that green solid. So there's a fourth example on how to find the volumes of solids using cross sections. In this case, it was a rectangle with a fixed height of 3.